Folks, picking up right here with this chapter 8 on tunneling. So I may have to turn this into 2 lectures. I suspect this will be pretty heavy. So if I have to turn this into, part A and part B, don't be surprised. So let's get right into it. Okay. So by definition, tunneling is energy leakage by penetration through a classically forbidden region. Okay, so what does that mean? Well, if we kind of think about the particle in the box problem that we were just working on, we put a particle in this box, okay, and we said there's infinite potential energy requirement to get out of the box. So the particle is stuck in there and it ain't going anywhere, okay? So that would be an idea of something being, classically forbidden. Much like if I imagine a closed container with a marble inside of it, right? And I can shake that container around, and the marble can't get out. Okay, it can't escape. Well, tunneling is this phenomenon where I have a particle and I've placed it, into a box, right? Like we've done before. But now there is not infinite potential energy to get out of the box. There's some amount, some finite amount of potential. And tunneling can be observed over certain distances and certain energies. And what that shows is the particle can actually transmit through this barrier and end up on the other side. So similar to this example I just described to you of having, let's say, a closed box and a marble inside, if I was shaking it out, if all of a sudden that marble just penetrated right through the container, right, and without damaging it, I'm not talking about like firing a bullet through a piece of paper or whatever. If it just appeared on the other side, it will have tunneled, okay? So that's what we mean by energy leakage by penetration through a classically forbidden region, okay? So here you can see this wave function is showing us, typical wave function, oscillating sine or cosine function. There is an exponential decay through the barrier. All right, so it is, dampened. And then as it comes out the other side, it returns back to its oscillatory pattern with less kinetic energy than it had before. Okay, so this picture isn't quite showing you everything that's going on. In actuality, we would have an incident wave as well as a reflected wave. So we could think of that in the wave-particle duality. If my particle, hit the barrier and then bounced back, okay, so we would expect to see a reflected wave. But also, the particle is able to transmit right through the barrier and then break on through eventually to the other side, okay? So it's a lot more complicated than just this simple picture. But all the same, using this one-dimensional concept and kind of borrowing some ideas from the particle in the box model, we can solve this problem. And that's what we're going to do next, okay?